Alright, part D, we're to the nearest whole number, we're trying to find the maximum number of mosquitoes on the island from day 0 to day 31. So show the analysis that leads to your conclusion. So we have to back it up with a little bit of work. In part C, we figured out kind of a formula to find out how many mosquitoes are on the island. We started off with 1,000 plus the definite interval from 0 we did to 31 to find out how many mosquitoes were on the island on the last day, but we're going to do it from 0 to t of r of x dx. And I'm going to write this as little r of t. Little r of t tells us the number of mosquitoes on the island on any given day. And we're trying to figure out what the maximum number is. So to figure out the maximum of that, we're going to look at the derivative of little r of t. Derivative of 1,000 is just going to be 0. Derivative of this rate, this definite integral, is just going to be capital R of t, right? Because we're going from 0 to t, this definite integral. Derivative of antiderivative cancels out. We just get capital R of t. So we need to figure out when is r of t equal to 0. That's the function we were given. And we should have that in our calculator for our y equals. So let's take a look at the graph. I want to find out when this is 0. So I set this up and I have a window from 0 to 31 because that's what our t value is. The y value doesn't really make a difference. I have it from -5 to 5. But we have two different points where we have a 0. So I'm going to go ahead and take that and put it in with our problem. So you want to sketch this on your notes. Alright, so now looking back at this, we want to find this 0. We can do second trace. We're going to calculate the 0, which is the second option. We need to choose a left bound. So this looks 1, 2, 3, 4, 5, 6, 7. So 7 is to the left of that point, and 9 is to the right. Enter. Enter one more time, and it's going to find our 0 for us. It's at 7.854. And we can find the other one, second trace, 0. Our left point over here, I'm just going to go ahead and put in 20. And the right point, 25, is to the right of that. Enter one more time. We get 23.562. So this is where the derivative of our original function is 0, where the rate is 0. If we look at this number line, and we're looking at the rate at which the mosquitoes change, at 7.854, derivative is 0. At 23.562, our derivative is 0. To the left of this, over here, to the left of 7.854, the derivative is positive, or the rate is positive. Then from here to here, it's below the axis, it's going to be negative. And then over here, it's going to be positive because it's above the axis. So we have a local max right here at 7.854, and here we have a local minimum. We're trying to find the absolute maximum. So I'm going to look at this local max and our two endpoints. So we want to figure out what is r of 0, what is r of 7.854, and what is r of 31. Well, r of 0 is pretty simple. That's the starting amount. That's going to be 1,000. If we look back at our equation, if we put 0 in here, 0 to 0, that's going to give us 0. It's just 1,000. For r of 7.854, 1,000 plus the definite integral from 0 to 7.854 of r of x dx. And then r of 31, we figured that out in part C. that should be 964. So we know that's not going to be our absolute max. It's either the original amount or what we get here at our local maximum. So let's figure this one out. We're going to do 1,000 plus that definite integral, so math 9, from 0 to 7.854 of y sub 1 vars, y vars function y sub 1, and we're doing that in terms of x. Now we could store that value in with the calculator to figure it out a little bit more accurately, but this is going to be enough to tell us that this one is going to be larger than the other one. We don't need an exact answer. We end up getting 1039.357, and that's going to be our maximum number. So 1,039 mosquitoes.